Why does splitting happen in NMR? So this is a molecule I've just drawn for educational purposes, but I want you to focus on these protons right here because it's important to know why splitting happens, not just the rule for n plus 1. So like I said, our splitting multiplicity is equal to n plus 1, where the multiplicity is the multiplicity of our signal to splitting, so to speak, and n is the number of neighboring hydrogens that are non-identical to the hydrogen that we're looking at. So I want to focus on these two right here. They have one neighbor right here. Now these would be a doublet. It would look like this. Why is that? So remember, the signal we see is because the proton has experienced the magnetic field applied by the instrument. So we just get a simple line like this if we had a singlet. Now where does the doublet come from? Remember, we have coupling between these. That's what causes the splitting. And vicinal alkyl coupling is roughly 6 to 8 hertz. And for this formula, we assume that it's always the same. We're operating under that assumption. So for this, we have one neighbor. So it's experiencing the field, okay, of the magnet. Now we split it because now there is a nuclei that could be either with or opposed to that magnetic field, creating two separate environments for the same signal. But there is an equal 50-50 chance of the neighboring nuclei being opposed or with, which is why we get a magnitude that looks like this. They're equal because there's 50%. Now let's take this a step further. Say we're looking at this proton. This would be a triplet. Well, where does that triplet come from? We are going to split yet again by assuming the same number of hertz, where now both are against. One is against, one is for. Now both are for. Now they're going to converge, where one is against and one is for. So now mathematically, we have 50% chance of them opposing each other and a 25% chance of them both being for, 25% chance of them both being against. And that's why these converge here, because these are the same coupling constants. We'll say 6 hertz. So that is why for a triplet, you see magnitude under the curve that looks like this, where that might actually not be to scale. Hold on. Where we have the center of our triplet is 50% of the area under that curve, and the sides are 25%. And then if you could, on your instrument, if you switch it from ppm to hertz, you would see that this distance right here would be 6 hertz on your signal. And that's how you get your coupling constant.